Yeah. So this is their point of view from the 2007 paper, and they do cohomology for these things because these people come more or less from knot theory, and so they are very interested in Rank co-cycles, and they use these cohomology operations for these Rank bialgebras also in order to do some knot invariants. Yeah. So they define Rank cohomology of Rank bialgebras by deformation. Yeah, I see. Okay. And so how do you, what do you mean by deformation? So for example, if you have any bialgebra with, so a vector space with a co-product and a product, yeah, product of any, in any way, then a deformation of it is triple of the same kind, but now everything is indexed by T, yeah, such that A T is A tensor over K tensor with the formal power series in the variable T, and then delta T goes from AT to delta T goes from AT to AT tensor AT, and mu T is a product, so it goes from AT tensor AT to AT. And then you want that when you quotient out T times AT, then you get A. Yeah. And so when you then you can write these deformed products as mu T is mu plus T times mu1 plus T squared mu2 and so on, and delta T is delta plus T with delta plus T squared delta 1 delta 2 and so on, and then you can ask yeah, for example, we want delta to be a co-product, yeah, so meaning it is co-associative, yeah, up to all orders, and we want that the co-product and the product are compatible in one sense. In which sense? When you first do the co-product and then the product, this is the same as doing first. So this is not possible. First the product and then the co-product, and you start on A tensor AT. Then you can also do first co-product tensor co-product, switch around factors, and then do the product. Yeah. So this is a compatibility between product and co-product, and then you want um, some identity for the product. Yeah, and so let's take the rank identity, but you could also take just associativity. Yeah, and so when you take the rank identity, it's the identity I just erased. So we have on the one hand we have this, and on the other hand we have delta, and so it. We have to switch around the factors in the middle, and then do the rec on both factors and the product behind. Yeah, and so when you have these are the demands you want at all powers of t in principle. But now you can come to the deformation cohomology when you ask them only up to order 1. Then you can get right away what you mean by a co-cycle. Yeah, and so let me show this to you. Yeah, get co-cycles by demanding these relations only up to order 1 yeah, and then for example, let me show what this leads to for rec cohomology. So when you have a rec bialgebra, and so what Carter, Kranz, El Hamdani decide to do is they deform both the co-product and the rec product. Yeah, but we in our paper later, together with Alexander Ordemann and Rivière, we do this deformation complex only for fixed co-product. Yeah, so the status of the theory is the following: Carter, Kranz, El Hamdani, Saito, they do the full deformation of all the structures, but they can go only up to order 3. Yeah, they only define cohomology up to order 3. Then it becomes combinatorially too complicated. What we can do is we can do it up to all orders, yeah, but in some special case only in the special case where the co-product is fixed and we don't know a general procedure which would work for all rec bialgebras. Yeah, and actually we fix it even to be co-commutative. Yeah, and so then let's have a small deformation. Yeah, and let me call this the rec product plus h bar omega. Yeah, let me call the deformation parameter now h bar, and then we want to have a h bar b h bar c is equal to a h bar b h bar a. Yeah, and so this gives a relation in powers of h bar, and in the up to order h bar to the zero, get back the self-distributivity. But the interesting term is in order h bar to the 1. Yeah. So what do we get in h bar? We get either we can take here the omega or here the omega. Yeah, but not in both, because we are neglecting all terms in h bar squared. Okay, there's a question. A rag bialgebra is a rag object in the symmetric tensor category of co-algebras. Is the cohomology of the rag cohomology in this? Yes, actually, I don't think there is a general theory for cohomology of rags in some weird symmetric tensor category. So this is what we are struggling with. Yeah, if you have a general definition, we would like to have it. Yes. Okay, in order 1, what do we get? Either take omega here or there. So on the one hand, we have omega A, B, C, and on the other hand, we have A, omega, B, C. And this must be equal to either have the omega here, 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 but only in one spot, because we are neglecting terms of h bar to higher orders. So omega A, B, A, C plus A, B, omega A, B, A, C plus A, B, omega A. Yeah, and so this is the co-cycle identity for rag bialgebra 2 co-cycles. Yeah, and so what we so starting from this example, we then generalize this to higher orders. And so in order to do so, yeah, so maybe I should reserve this formula and then go back to this formula when we have the general definition. So in order to implement this, in our framework where we have a fixed co-product, we need co-derivations. Why do we need co-derivations as co-chains? Because recall when we have a morphism of co-algebras, this means that when we do first phi and then the co-product, let's say phi dot from C to D, this is the same as doing first the co-product in C and then phi and the phi. Yeah, and so a co-derivation is the infinitesimal perturbation or deformation of a morphism. Yeah, so what I mean by this is that when you take a morphism of the kind T plus H bar C, yeah, what does it mean up to order H bar to be a morphism? Yeah, morphism up to order H bar. Yeah. In order H bar 0, yeah, there's a question. No. So we just get that identity in the morphism. But in order H bar, we get now that we either have delta C here, or we can have an H bar either here or there. Yeah, so either we have an H bar here, then this is C tensor A plus F tensor C. Yeah, and this is what is meant by a co-derivation. Co-derivation along the identity. Yeah, and you can do the same computations with a co-derivation along the morphism. Yeah, and so C goes from C to D. It is a co-derivation along phi. If yeah, we have this here. So this is D, maybe. C. So the co-cycles we want are infinitesimal perturbations of a morphism. Yeah. So this is kind of in deformation theory, this is always the case. Yeah. And so we want co-derivations with respect to which morphism. And in fact, the morphism phi we need are mu. Let's say mu to the 1 is the identity, mu to the 2 is mu, is the rank product, and we in the axioms of being a rank by algebra, we had demanded that this that the rank product is a morphism of co-algebras. Yeah, so this makes sense, and then we go up higher. Yeah, actually this way, and then by induction we find n plus 1 to be the mu, n to be mu composed with mu1. Oh no, it was mu1. Tensor u n minus. Yeah. these are the morphisms of co-algebra which we want to put here. Yeah, and so the cochains will be co-derivations with respect to these morphisms. And now I can. Oh yeah, I erased. Sorry, I erased what I want to do. Conserve, but so the deformation complex of a graph algebra of co-commutativeness is so C. I think I call it C. C of C from the C is the co-derivations on the C to the n with values in C to the with values in C, yeah. With respect to the morphism mu to the n, yeah. And the differential is like the rack differential for the first term. But now we have coefficients, yeah, for the deformation cohomology. You always have as coefficients the adjoint coefficients, so the coefficients in the object you're deforming, yeah, and so we need another term in the cocycle, in the coboundary formula. This is n plus 1, and these have the explicit formula, the following: I the 1 n of C of omega so we have mu I of R1, and now I have indices for these elements, so I'm not putting the Sweedler indices underneath, but I'm putting the Sweedler indices upstairs. Yeah, so just for notational convenience. So I duplicate all these elements R1 up to Ri minus 1. The first part of the Sweedler formula I put here, and then the second parts go into omega. And the i's one is omega. Yeah, the i's one is over here. It's not duplicated. And so these are the action terms. Yeah, it's on the outside. This is the rag product in the rag bialgebra where we are heading. Yeah. And now come the terms where the rag product comes into play, and these are also like in the rag cohomology, Ri1 acting on Ri1, and then Ri is duplicated n plus 1 minus I times and acts on n plus 1 in the last spot. Yeah. So these are the terms we know already from the rag cohomology, and now we have an extra term here, which which comes from the adjoint action, yeah. And in the adjoint action, we also have a term acting from the other side. Two, and to the 2 and the Rn plus 1 without. Yeah. So this is a very complicated looking complex. But in fact, it is a complex. Yeah. Yeah. Is a differential yeah, thanks to the cubical identities. Yeah. Yeah, so this is a little bit more complicated, and I put it down in the lecture notes, like in our article. The cubical identities which we saw were about these two parts of the co-boundary operator, and they still show that this adds up to a differential. And then what we show furthermore is that the interaction of this one with these two is such that the whole dr becomes a differential. Yeah, and so we get a deformation homology H C. And now maybe we can go back and look at what we have in degree 2. Yeah. So in degree 2, we have the DI. This is the DI1. Yeah. The DI1. 2 is on the one hand we have R1, R2 acting on omega 1, 2. No, that's not correct, because I'm just going, okay, let's take I equal to 1. And we go I equal to 1, then we don't have these. And we just have oh yeah, I need 3. Now I equal to 1. So it starts here from 2 and 3. Yeah. Okay. And then we need 2, 1. And we get 4. I equal to 2. We just have the omega 3 here. So we have to do it. that is this one. And so what did we have before? Did we get the terms we need? Yes, these are two of the terms which we had here. Yeah, and maybe this can be enough to tell you we get exactly the 5 terms which we had in the co-cycle identity. 5 terms together with this auxiliary operator. Okay, so when talking about deformation cohomology, we need why did we introduce a deformation cohomology? In fact, we introduced a deformation cohomology because we wanted to express a deformation. Yeah, we had a deformation and we wanted to know in which deformation complex it lives. Yeah, so an example of the deformation. So this is together with Leibniz in 2015. When you have a Leibniz algebra, yeah, then its dual space is a smooth manifold. And you know from Lie theory that the dual of a Lie algebra is a Poisson manifold. Yeah. So what we asked, or what Alan Weinstein asked, is when you take a Leibniz algebra, in which sense H star is a Poisson manifold. Yeah. And we had one answer to this question in 2015. So is a generalized Poisson manifold in the following sense. Actually, we have a bracket, and the bracket is kind of very strange looking. For 2 functions on H star, evaluated on psi of H star. The bracket is F of 0, PG of psi, and then evaluated against the element psi. Yeah. So the linear term in a smooth function on H star is just an element of H. Yeah. And so it makes sense to take the bracket of these 2 elements of H and then evaluate against an element of H star. So this is a very strange looking bracket, but it comes out of our theory that this is the generalized Poisson bracket which we have on our generalized Poisson manifold. Yeah, and so in this work we had a maybe there are questions. Yes, I see a bialgebra, but the deformation, yeah, exactly. Yeah, wrong. Yeah, you're talking about Gerstenhaber-Schack algebra, Gerstenhaber-Schack cohomology, and this is kind of the cohomology of an associative bialgebra. And let me come to this later. Yeah? In some sense, it is a very complicated object, but I can say some things about it. Let me say them later. Okay, here we are Benoit Derain comes from symplectic geometry, and so we were doing this deformation business first in a very symplectic way. Yeah, and the symplectic version of it is that we take the cotangent lift of the rank product I already showed to you, yeah, of this product, and then interpret it as the symplectic micromorphism. Yeah. So these objects come from the following theory. Symplectic geometry is not very well stated in a category framework. Yeah. And so Weinstein and collaborators, Weinstein, Derain, and Felder, I think, thought about how to put it in a category framework. And so one needs to have not the category of all symplectic morphisms. Yeah, then you don't have fiber products. You don't have the category axioms. Yeah, but only germs of morphisms. Yeah, with germs of morphism it works. And this is where the micromorphism comes from. Yeah, it's only a germ of a morphism. Yeah, and so this rag product here, we talked already about this, is not a kind of a global rag product which is interesting, but the germ of it is very interesting and characterizes the Leibniz structure. Yeah, so then there's a general procedure how to obtain from a symplectic micromorphism and a Fourier integral operator. So this is then the phase factor in a Fourier integral operator. And its asymptotic expansion gives then a star product. Yeah, and so in this way we obtain the star product as a deformation, yeah, of a certain Poisson bracket, yeah, on the dual of the Leibniz algebra. Yeah, but let me not go into the details because together with Alexandre Bordemann and Rivière, we have put this in a more algebraic framework. Yeah, the algebraic version of it. So this is kind of the differential geometric version of it, and in some sense it's very natural because when you do all these steps here, yeah, with a Lie algebra, and you take here the Baker-Campbell-Hausdorff formula, this is something like the Baker-Campbell-Hausdorff formula in the Leibniz setting. Yeah, when you take the Baker-Campbell-Hausdorff formula, you interpret it as a symplectic micromorphism. You put it as a phase factor in the Fourier integral operator and do the asymptotic expansion. You get the good star product, the star product of Simon Good. Yeah, and so this is very well known to be related to the integration of Lie algebras into Lie groups. And so we did kind of the same procedure, but with this rag product, yeah, and then we get the star product deforming this generalized Poisson bracket. But the explicit formula And this is in our paper with Alexander Bordemann, Rivière and me, is for two C infinity function on the dual of H. On the dual of H, yeah, we have the following: this rec product, this deformed rec product for alpha in H star is big star. And then you have some operators in here. Yeah, the first operator is the differential of f with respect to alpha r1, alpha r, evaluated in 0. Yeah, and this is the same 0 as here. Yeah, this is why the Poisson bracket we get from here is of this strange form. And then we have some add operators, add I1 and IR evaluated, acting on G and evaluated in G. Yeah. So this is our star product. And you can interpret it as a deformation of the red product. And so I should say that these add operators here are defined as follows. Yeah, you take a basis here. Yeah, alpha is alpha 1 to alpha n, and n is the dimension of H. Yeah, I did not say, but we are always working with a finite dimensional Leibniz algebra. Alpha k, and here are the structure constants of the Leibniz algebra H, and F is going to be evaluated. Yeah, these are these add operators. Yeah, add because the bracket comes in. Yeah. These are kind of the same add operators as for the algebras. Okay, and so this is what I wanted to say. We had a deformation, and we wanted the deformation complex, which has all these partial elements as co-cycles. Yeah, and so we can show with this, gives a deformation on the trivial product, which is just x, y is epsilon of x, y, yeah? On the symmetric symmetric algebra on H star, yeah, meaning when we get down from C infinity functions and take only the polynomial C infinity functions, yeah, then we get deformation in the sense above of this trivial rag problem. And there's a nice relation. There's a nice relation between this very complicated looking rag product, deformed rag product, And the rank product I already told you about, the e to the h at x of y. And this is this relation where we denote by x at the c infinity h star and the function of alpha is alpha of x. Now, x is in h bar, is in h, and so alpha is in h star. So this is we see elements of h as functions on the dual. Yeah, and so when you take the exponentials of these functions and you do this complicated star product, then you get just the exponential of this rank product I told you. Okay, so kind of this defines the deformation cohomology and gives you a reason why to study deformation cohomology, maybe. So what is largely unexplored is the relation of this cohomology theory to the cohomology theories we studied yesterday and the day before. Now, we don't know the relation, the good relation to Rack cohomology or the relation to Leibniz cohomology. All we know is, and I already told you this, from the cohomology of a Lie-Rack, you can, by differentiation, go to the cohomology of the Leibniz algebra. And now I will show you the theorem which tells you from the cohomology of the Leibniz algebra, you can go to the Rack bialgebra cohomology in this sense. Yeah. Okay. This is all we know, and all the other relations which may be there between these cohomologies are still to be discovered. Yeah? So I encourage you to study those. So let me show to you the theorem on and me in 2019. Not very difficult theorem. Consider the rank bialgebra that we see with k times 1 plus h associated to a Leibniz algebra h. The Leibniz complex with adjoint coefficients embeds into the Rack bialgebra complex. Actually, once again, this is a very easy theorem. So you see, all the theorems we can prove about the relation between these cohomologies are very easy. The difficult theorems are still to be found. Yeah. Okay. Proof is the following. So take a Leibniz project. Yeah, we have to extend it to a co-derivation on the Rack bialgebra complex of this Rack bialgebra. Yeah, this is what we first have to do. And extended to co-derivation, so co-chain in C E with K 1 plus H I F of R1 Rn is, yeah, and these R1 Rn, they are lambda 1 x1, lambda n xn. Yeah, one component in this one here and one component here. And then you can just take f on x1, xn. This is kind of all you can do. Yeah, and then project it down to h. Yeah, so first of all, these are co-derivations along u to the n. Why? And to be a co-derivation along u to the n means that delta C composes omega is omega tensor mu n plus mu n tensor omega composed with delta C to the n. Yeah, so why is this the case? Yeah, this is once again very easy because look here. When we take this omega on any elements here, will be an element of H. Yeah, and as an element of H, it will be primitive. Yeah, and so this gives just on the left-hand side we get omega tensor 1 plus 1 tensor omega of these elements. Yeah, and so we have to see that on the right-hand side we also get only this term. Why is this the case? Because these cochains here are zero if I only put the ones in here. Yeah, if I only put multiples of the unit in omega, then they are zero. So so first of all, this co-product here mixes, yeah, all the x1 to xn and the ones here. Yeah, so you get very long expressions where there are ones, tensor 1, tensor 1, tensor xi, tensor xj, and so on. Yeah? And so on all these elements, you evaluate this here. Yeah, but only if all the ones, yeah, if no one comes into the omega, yeah, then this can give something non-zero. So if all the x1 to xn are in omega, all the ones have to be here. And here on the mu to the n, it is 1 rex on 1, rex on 1, rex on 1. So it gives only 1. Yeah, so this is 1 tensor omega. And here the same. Yeah, if one of the ones goes into the omega, then it gives 0. Yeah, so all the x1 to xn must be here, and all the ones here, and so it once again it gives omega tensor 1. So these are co-derivations.
So the image of F is in H. Why do we still need to take a projection to H?
Oh yes, maybe you're right. Maybe we don't need the projection. Thank you. That's right. Yeah, we need something else. We need the embedding of H into C. Yeah. Sorry. Yeah.
Okay. Okay. Thank you.
Okay, and now compare terms in the co-boundary formula. Yeah, so we have this term here. I to the R1 and 1 and I minus 1 I omega I 2 I minus 1 2 I plus 1 2 and 1. So here it's actually the same thing. Yeah, your if you have the RIs, yeah, once again they give ones or elements of the Leibniz algebras. Yeah, so if any of the ones is in the omega, then this gives 0. Yeah, so we need all the elements of the Leibniz algebra here, and so we can only have ones here. And so what this gives is Ri omega R1 R-1 I plus 1 and this in the rag bialgebra associated to a Leibniz algebra, this is just a bracket. Yeah, and so this works also for the other terms. For the other terms, we get the similar situation. It's J0 and omega. We have omega R1 minus 1 J1 acting on J plus 1 J n plus 1 minus J acting on yeah. And so once again, if the ones are yeah, so here we are only taking the co-product of Rj. Yeah. So we will have here many ones and then one xj in H. Yeah. So only so for every term here we have 1 times the bracket term, and all the others where there are the ones will be just the elements. Yeah, so this gives omega R1 J minus 1, and so if the element is here, it gives you Rj plus 1, but then all the others are without bracket, yeah, because here are the ones then, yeah, and you have then the term J plus 1, J plus 2, J plus 3, and so on, n plus 1, yeah, because now the element of the Leibniz algebra was here, and all the others were with ones. And you go on until the last term. Minus 1 J plus 1 J and so you see These are the action terms in the Leibniz co-boundary operator. These are the bracket terms in the Leibniz co-boundary operator. And there's one action term missing. It's the action term from the right. Yeah, and this comes by this additional operator. Yeah. So the additional operator gives the last term in the Leibniz co-boundary formula. One. Yes. And actually, I found still some typos in my lecture notes. I corrected them, and I've put a new version on the web this morning. So maybe you would like to add a new version. So here, once again, the reasoning is always the same. When we do the co-product on R1 or on Rn-1, yeah, all these elements are primitive. Yeah, if there's only a factor 1 in there, then it will give nothing. So there must be a factor in the Leibniz algebra, and then they are primitive, and so there's one factor with 1 and one factor with the element of the Leibniz algebra. So if but all the elements of the Leibniz algebra must be here, yeah. Otherwise, omega evaluated on it will give 0. So this is in fact R1, Rn-1, Rn, and then the rank product is once again the rank. Yeah? So this gives the action term from the right in the Leibniz co-boundary formula. And with the other terms together, we get the Leibniz co-boundary operator. Okay. So now let me, maybe you have questions. Otherwise, I talk about the outlook. Yes. So what happens is Leibniz algebras are algebras over an operator. Yeah. What does operand mean? Yeah. An operand is some. So it was a little bit like with categories. Yeah. In categories in the beginning were a device to assemble theorems in some mathematical theory. In a nice and handy way, yeah. But then later on, categories were studied as algebraic objects of themselves, yeah. And so for the operands, it's a little bit the same. In the beginning, operands were studied as things which were detecting like iterated loop spaces, but they were not so much investigated for themselves. But nowadays, they are fully fledged algebraic objects, and they many people study operad. So what is an operad? An operad is an algebraic structure which parametrizes the operations of your algebra. Yeah, and so there you can see it as an algebraic structure. So as an algebraic structure, there's a free operad, yeah, free operad on some generators, and then you divide by relations, yeah. And so what is a free operad? The free operad is just it's just trees with your operations. Maybe several branches and several operations like this. Yeah. And so then dividing out the relation tells you which kind of algebraic structure you want to study. Yeah, let me do an easy example. Yeah, for the associative algebras, I'm cheating a little bit, because in the framework of symmetric operads, you always have an action of the symmetric groups on it. Yeah, and so the space of generators is just one operation like this. Let's say, yeah, k times 1, yeah, because everything is k linear, and the relations are of the kind associativity. Yeah. So in this sense, Leibniz algebras are also algebras over an operad, and so there's a whole theory coming with operads, theory of co-duality, which tells you, for example, that the Lie operad is dual to the commutative operad. Yeah, the algebras over the commutative operad are the commutative associative algebras. Algebras over the Lie operad are the Lie algebras. And so this relation tells you, for example, that the cohomology of a Lie algebra is a commutative algebra. Yeah, this co-duality between com and Lie. And so these relations in the framework of operads are kind of easy to handle, yeah? Or at least there is theory about it, and you can use this here. So what is so first of all, I think RAGs are, to my knowledge, not algebras over an operad, but they are kind of very close to groups. Yeah, so all the methods you can do with groups and the cohomology of groups you can do with RAGs, and this is why I cited to you the paper of Chimit. RAG cohomology is equivalent homology. Equivalent homology. Quillen devised a framework, a very general framework, where you can, in which to interpret cohomology as derived functors. Yeah, so you have a model structure on the simplicial enrichment of your category, and then the functor of abelianization can be interpreted as a functor which can be derived, and the derived functor gives then RAG cohomology. Yeah, so RAG cohomology, like group cohomology, can fit into a Quillen frame. Yeah, actually, for the operatic cohomology of algebras over an operad is also a Quillen cohomology. Yeah, it is Andre Quillen cohomology. So at least for the operads we are interested in. And so the question is somehow, how do we deal with ranked algebras? Yeah, how to fit ranked bialgebras, ranked bialgebra homology into an operatic or equivalent framework. Yeah, and this is not so easy. Yeah, what happens is already for associative bialgebras, this was very difficult. Yeah, associative bialgebras are not algebras over an operand, yeah, but they are algebras over a properand. Yeah, and so what is a properand? It is something where you not only have operations like this, yeah, but you also have operations in the other sense. Yeah, so you have, yeah, you not only have always one output, several inputs, but one output, but in properands you can have operations where there are several inputs and several outputs. Yeah, so where these are so-called S modules, yeah, you have an action of the symmetric group on the inputs. Here you have an S bimodule. You have an action on of the symmetric group on the inputs and on the outputs. Yeah, and so these are much more difficult to handle, but Markel and Merkulov, Valette understood how to formulate Koszul of the properand of associative bialgebras. And so the right thing is not to actually Koszul theory is this Koszul duality theory is a theory which comes from Koszul duality of associative algebras. And these associative algebras were always quadratic algebras. Yeah, so meaning generated by generators in degree 2 and then with relations of degree 3. Yeah, and so there is a duality first of these associative algebras, and operands are kind of very close to associative algebras because they are also monads in some category. And so Ginzburg and Kapranov were then transposing this Koszul duality theory for quadratic algebras into the framework of operands. Yeah, and so Markel and Merkulov-Valette thought about how to transpose it further to properands. Yeah, and so here the problem is that for the properand of associative bialgebras, you have the following relations. You have on the one hand associativity and co-associativity, but and these are kind of the nice relations, but you also have the bialgebra axiom. Yeah, and the bialgebra axiom tells you the bialgebra axiom tells you when you have you have two inputs, let's say, you do a product and then you do a co-product. This is the same as doing first co-products on both of your inputs, interchanging the middle ones, and then doing the products. Yeah, this is a bialgebra axiom, or otherwise said, this is an axiom that the co-product is a morphism of algebras, or that the product is a morphism of co-algebras. Yeah, and this is the most difficult to handle, because here we have only two operations at each time. Two operations or co-operations. Here also two operations, but here we have four operations. Yeah, and so in causal duality theory, this kind of graph does not can come into. Yeah, and so Markel and Merkulov-Valette developed a theory where you have what they say homotopy causalness. Yeah, meaning that even when you have graphs which show you that you cannot be causal, can still be causal in some sense. Yeah, and this causalness in some sense can still imply that you have canonical resolution, you have co-fibrant models and all that. And so what we were trying with a thesis student was to show this type of weak causalness, this homotopy causalness, for the properad of rank bialgebras. So the properad of rank bialgebras is generated by an operation and a cooperation. Yeah, and the relations are. I'm always switching between. Let's say this is a cooperation. So you have co-associativity. You have the bialgebra axiom. And you have this strange axiom which tells you when you oh yeah, I'm let's see. When you're starting with three of them, and then you do one product and another product. This is this is the rank identity, meaning A, B, B is A1, B, A2, yeah, and so you have a perfectly defined properad such that the algebras over this properad are your rank bialgebra. I'm cheating a little bit because we did not incorporate units or co-units. Yeah, so up to units and co-units, this gives the right notion of algebras. And so my student showed that we come close to causalness, but to this homotopy causalness. But unfortunately, there's still one thing we cannot conclude. Yeah, so for the moment, this is kind of obstructed. But so this is how far we could come, from my point of view, to having a good framework for the cohomology of rank bialgebras. And maybe in the last 5 minutes, I can comment on do some wishful thinking, yeah, what we would like to have. In fact, Well, it's not a good idea to put it on this blackboard. So Daniel Quillen was a very influential mathematician of the 20th century, and he has a paper on rational homotopy theory in 1969, I think. So what he proves there was that topological spaces, one-connected topological spaces, can have models, for their rational homotopy theory in terms of differential graded Lie algebras or in terms of differential graded commutative algebras. These are the Solomon models. And so what he showed was this theorem as a sequence of pairs of adjoint functors, and nowadays we would say Quillen adjoint functors between model categories, and these Quillen adjoint functors then induce equivalences of categories, and the last equivalence of category, the chain of equivalences of categories would then prove his theorem, and so the chain of adjoint functors is the following. You have here one connected topological spaces, and here one connected simplicial sets, and between topological spaces and simplicial sets you have the usual functors of geometric realization of the simplicial set is a topological space, and the singular chains of topological space are a simplicial set, and these two functors are Quillen adjoint and induce an equivalence between the homotopy categories of these two model factors. And so the chain goes on further. You can go from simplicial sets to simplicial groups. There is a sort of Kahn loop space, associating to a simplicial set, a simplicial group, and you have a classifying space functor going in the other direction, and those two are again a pair of Quillen adjoint functors, inducing an equivalence of the corresponding homotopy categories. And go further. Now we go to simplicial complete Hopf algebras. Simplicial, everything is simplicial, complete Hopf algebras. And from groups to Hopf algebras, remember what we did in the beginning. You take the group algebra of your simplicial group, and in fact you can you have to complete, you complete with respect to the augmentation idea, and then you get a simplicial complete Hopf algebra, and when you take, this is a functor of group likes I told you about. When you do this for a simplicial complete Hopf algebra, you get back a simplicial group. And once again, these two are Quillen adjoint functors inducing an equivalence of the corresponding homotopy categories. And so here you don't see anymore. Here is simplicial Lie algebras. And these ones here always mean a certain connectedness condition, which comes from the fact that we are dealing with one connected topological spaces. So simplicial Lie algebras, and then you can go one step further to simplicial co-algebra. And the functors here are the primitives and the completed universal enveloping algebra, and here the functors are from Lie algebras to co-algebras. This is the Chevalier-Eilenberg complex, and from co-algebras to Lie algebras, maybe I don't remember, but this is not so important. So my wish would be to have such a chain of Quillen adjoint functors. Now, here we put the cubical simplicial sets, cubical simplicial set here corresponding to the simplicial sets, and then we have the functor, at least we have a functor of classifying space from simplicial racks. Yeah, this classifying space is the classifying space of Fenn, Sanderson, and Rourke. Fenn, Rourke, and Sanderson. We go to simplicial racks, and then we go to, you can imagine, we go to simplicial complete rack bialgebras, go to simplicial Leibniz algebras, and then go to maybe don't have the last step. Or no, here we are in simplicial Zinbiel algebras. Yeah, and so my wish would be to have all this chain of Quillen adjoint functors also in the cubical business, yeah, together with the racks replacing the groups, the rack bialgebras replacing the Hopf algebras. Maybe we need an antipode, yeah, which we don't have for the rack bialgebras yet. The Leibniz algebras replacing the Lie algebras, and so on. Yeah, and so I think this can still describe topological spaces, yeah, because we know from Jean-Pierre Serre's thesis that the cubical simplicial business is as good as the usual simplicial business. Yeah. So, okay, thank you. I will stop here.
Okay, thank you very much. Very ambitious. Yeah. Yeah, very good plan. Okay, so are there any questions or comments? Okay, maybe first I ask a question. So about that G star, maybe H star. So maybe the dual space of a Leibniz algebra. So you consider the deformation theory. So I'm wondering. So for the algebra, we know that the dual space G star is a Poisson algebra. Namely,
yes,
there's a Lie bracket, there's a graded commutative algebra, so that it is a Poisson algebra. And for Leibniz algebra, is there a similar algebraic structure?
Yeah, unfortunately, the Poisson bracket is kind of not the good one. Yeah, it's not a very nice Poisson bracket, but it's a generalized Poisson bracket. So what we had as a generalized Poisson bracket is for C infinity functions on H star, we have that this generalized Poisson bracket on alpha is
yeah. So we can only have this Poisson bracket. So are there similar objects?
But generalized Poisson.
Yeah, generalized, because at least it is not skew-symmetric. I mean, so there should be a similar algebraic structure for the graded commutative algebra also, not only the bracket.
Interesting question. Yes, I don't know. No. In some sense, we answered these questions in our paper with Martin Bordemann and Salim Rivière and Alexandre Charles Alexandre, because we have a bracket,
this, we have
on the dual, on the symmetric algebra, on the dual of H star. Yeah, so this is kind of what you want.
Oh, on the symmetric algebra.
Yeah. We first have it on all the C infinity functions, and then we restrict to the symmetric algebra. This is what we do in the second paper, in the more algebraic paper. Yeah.
Okay, so on symmetric algebra, so it's
And we show that it is a rack bialgebra.
Okay. Okay, so instead of the usual Poisson algebra, so you're between a rack bialgebra. Okay.
Yeah,
okay.
It's not a Poisson algebra. It is a
Yeah, definitely it is not Poisson. There has to be a similar algebraic structure. Yeah.
Exactly.
It's
we try to follow the analogy up to the end. Yeah, exactly.
Yeah. So it's very interesting. Okay. There's another question in chat. So
for topological space, use cubical simplicity sets or using usual simplicity sets to study the homotopy theory of the will make any difference? No, I don't think it makes a difference. Yeah, it's kind of a different mathematical tools to describe the same things. In the thesis of Jean-Pierre Serre, he computed the rational homotopy of spheres, in 1956, if I'm not mistaken, and he already saw that the simplicial theory was not good enough for his purposes, and so he had to develop the cubical simplicial theory in order to do what he did in his thesis. So this is kind of forgotten nowadays, but it is a very interesting point of view, and I think it is the right point of view to deal with the racks.
Okay, thank you. Okay, so are there any other questions? Okay, so in this mini course, Professor Frederick Wagman systematically introduced Leibniz algebras, racks, rack bialgebras, and their cohomology theories, and in particular established some important relations between them. But as mentioned by Professor Frederick Wagman, so there are still many open questions. So I think everyone get benefit from this mini course. Okay, so I think finally we give our warmest thanks to Professor Frederick Wagman. Thanks a lot for your contribution. Thanks.
Thank you very much. Thank you very much for listening and for inviting me.
Okay, thank you. So maybe, so we stop it here, and bye-bye.
Bye-bye. Thank you.
Bye-bye. Bye-bye, everybody. Bye-bye.